We know that the ammeter reading is 0.5 ampere in diagram 1, so we can just label, and the voltmeter reading is 3 volt. Okay, so in this case the voltmeter reading is actually the voltage of the cell as well, so this is 3 volt. Okay, now let's look at diagram 2. The cell that is being used is the same, so this is also 3 volt. Okay, so we want to find out what is the ammeter reading. Before that, we need to know what is the resistance of each resistor. Okay, so we come back to diagram 1. We are given the voltage and the current, so we can find the resistance is equal to 3 V over I, which is 3 volt divided by 0.5 ampere, so that will give us 6 ohm. Okay, so now in diagram 2, we know that this resistor is 6 ohm and also 6 ohms here. Okay, so to find out what is the overall current that flows through the cell, we can combine these two resistors, okay, into one. So how do we do that? It will be 1 over R is equal to 1 over 6 plus 1 over 6. So 1 over R is equal to 2 over 6. Then we simplify it, we will get 1 over 3. So the total combined resistance of this parallel branch, it will be 3 ohms, because we have to flip this upside down. Okay, so now this is 3 ohm. We have the voltage as 3 volt and the total resistance here as 3 ohms. The current, we can use the formula V over R. So it will be 3 over 3. The current should be 1 ampere. Okay, so now let's look at the options. We should go for the option that is 3 volt and 1 ampere for the ammeter reading. So the answer should be A. This is a series circuit, okay, with a EMF of 9 volt, and we have two similar resistors as well as a light bulb that is connected in series. Then the voltmeter across one resistor, it reads 2 volt. That means the voltage across the other identical resistor should also read 2 volt. We are asked what is the potential difference across the lamp. So in a series circuit, the EMF is being distributed across all the resistance. Okay, so the voltage across the lamp, let it be V. We can say that 2 volt plus 2 volt plus V, it should be equal to the total EMF of 9 volt. Okay, so over V, we can take 9 minus 2 minus 2. That will be 5 volt. A. Okay, to find the cost of electricity, right, we have to find the energy consumed in kilowatt hour. Okay, that we will need the power in kilowatt and the time in hour. Okay, so what is the cost of using this iron at maximum power rating? Okay, we know that the power range of this iron is between 1000 to 1200 watts. Okay, so maximum power, that means it must be operating at 1200 watts. And 1200 watts, to convert it to kilowatt, is actually 1.2 kilowatt. So we have 1.2 kilowatt multiplied by the number of hours, which is 10. So we have 12 kilowatt hour. Okay, so if electricity costs 7 cents per unit means per kilowatt hour. So the cost, it will be 12 times 7. That will give us 84 cents. Answer C. Okay, referring to this diagram here, the switch must always be connected in between the live wire and the appliance, which is the heating element here. So the answer is B. Okay, what is the reason for doing so, right? Is that when the switch is open, we want the appliance to be safe, as in it should be safe for the user to touch it. Okay, so in this case, if the switch is placed here when it is open, it disconnects the high voltage of the live terminal from the appliance. So the appliance will be at 0 volt. So it will pose no danger to the user at all. Okay, for this question, right, we just need to recall that for a magnet, the field line will go out from the north and it will come in from the south. Okay, so in this case, for the first magnet here, the field line is coming in, so we can deduce that this is a south, and the field lines are going out, so this should be a north. So for this side, the field lines are coming in, so it must be a south, and this side it should be a north. Okay, so we have north, south, south, north. Okay, so the answer should be D.